Welcome to today's lecture. So, in the yesterday's class we talked about coding for discrete memoryless sources. So, now we are going to talk about how we can do source coding for discrete stationary sources, discrete stationary source, and we'll talk about discrete stationary sources with memory and how we can exploit the memory for. In the first lecture today, I am just going to describe what is discrete stationary source and the properties of discrete stationary source, and I am going to talk about how we can encode positive numbers using some prefix free code. So, that is basically alias code, and in the next lecture I am going to talk about block to variable length coding for a discrete stationary source, which is the Elias-Williams code that I will talk about. So, I will talk about discrete stationary source and its properties in this lecture, and then I will talk about how we can encode positive numbers using prefix free code, which is the alias code that we will be talking about. So, a k-array discrete stationary source is a device that emits sequences ui of k-array random variables such that for every n greater than equal to 1 and for every L greater than equal to 1, the random vectors u1, u2, u3, ul and un plus 1, un plus 2 to un plus L have the same probability distribution. So, basically we are talking about that the distribution is stationary, right. Now, we say a discrete stationary source has a finite memory mu if for all n greater than mu this condition applies. So, probability of un given u1, u2, u3, un minus 1, it depends on past mu values. So, this is equal to probability of un given un minus 1, un minus 2, un minus 3 up to un minus mu, and this holds for all choices of u1, u2, u3, and mu is the smallest non-negative number such that this relation holds. Now, as you can see, a discrete memoryless source is a special case of this, for the case when mu is basically 0. Now, for a discrete stationary source with memory mu, the entropy of un given u1, u2, un minus 1 can be written as h of un given u1, un minus 1, un minus 2, un minus mu. This follows from, we can write this probability as this, right. So, in the entropy expression, when you replace this by this, what you are going to get is this. Now, in case of a discrete stationary source, how do we describe basically uncertainty? So, there are two ways of doing it. One way of defining this is uncertainty per letter of output sequence. So, we define this as uncertainty per letter as entropy of u1, u2, u3, ul divided by L, and another way of defining this uncertainty per letter is we define in terms of conditional entropy. So, entropy of ul given u1, u2, u3, ul minus 1. So, these are the two ways in which we could describe the uncertainty per letter for a discrete stationary source. Now, we are going to show you some properties of these descriptions, okay, and we are going to show that when L goes to infinity, this is same as this, and this is known as entropy rate of the source. So, we are going to show you these properties in the next slide, and we are going to prove the properties. Are these definitions clear? So, we have described a discrete stationary source, we have described a discrete stationary source with memory, we have said entropy for a discrete stationary source with memory is given by this, and then we have talked about two measures in two ways of describing uncertainty per letter for a discrete stationary source. So, if U1, U2, U3, UL are basically output of a discrete stationary source, then these properties hold. Uncertainty in UL given U1, U2, UL minus 1 is less than uncertainty per letter, the way we defined it here, is less than equal to this. Okay. Then H of UL given U1, U2, UL minus 1 is non-increasing as L increases. What do we mean by non-increasing? So, basically as L increases, so H of UL plus 1 given U1, U2, U3, UL will be less than equal to H of UL given U1, U2, U3. So, as L increases, this basically is less than equal to basically UL plus 1 given U1, U2, UL is less than equal to H of UL given U1, U2, UL minus 1. Similarly, this is also non-increasing as L increases. And finally, as I said, when L goes to infinity, this is same as this is same as what we call entropy rate of a discrete stationary source. So, let us now prove these properties of the discrete stationary sources, and how do these properties, let us prove these properties. So, we will first prove property number 2. To show that this is non-increasing, what we need to show is H of UL plus 1 given U1, U2, U3, UL is less than equal to H of UL given U1, U2, UL minus 1. This is what we have to prove. So, we start with this H of UL given U1, U2, U3, UL minus 1. We are saying this is less than equal to H of UL plus 1 given U2, U3, UL. Why? Exactly. This was conditioned on additional U1, here it is not conditioned on U1. So, conditioning cannot increase entropy. So, H of UL plus 1 given U1, U2, UL is less than equal to H of UL plus 1 given U2, U3, UL, right. Now, I am saying this is same as H of UL given U1, U2, U3, UL minus 1. Why? This is a stationary source. So, remember I said for a stationary source, so this distribution of, so this will be same as UL given U1, U2, UL minus 1. This follows from the fact that this is a stationary source. Okay. So, what I have shown you is uncertainty in UL plus 1 given U1, U2, UL is less than equal to uncertainty in UL given U1, U2, UL minus 1. That means, as L increases, this is a non-increasing function of L. Okay. So, we have proved property number 2. Now, let us go to property number 1. So, we have to show that 1 by L of this quantity is greater than. So, let us start with this joint entropy of U1, U2, U3, UL. Now, this can be written as H of U1 plus H of U2 given U1 plus H of U3 given U1, U2 plus up to H of UL given U1, U2, U3, UL minus 1. Which property did we use? We used the chain rule, right. So, using chain rule we can write it this way. Now, the next claim I am making is this whole summation is lower bounded by L of H of UL given U1, U2, U3, UL minus 1. Why? I am using property number 2. What does property number 2 says? As L increases, this is a non-increasing function. That means, as L is increasing, this is less than H of UL minus 1 given U1, U2, U3, UL minus 2, which is less than this. So the smallest term here is this, and there are L such terms. So this is upper bounded by L H of UL given U1, U2, U3, UL minus 1, correct. Now we divide both sides by L. So what we get on the right hand side is this, and the left hand side we get this, and the right hand side we get this. So we have proved the property number 1 as well. Fine. Any questions? Okay. Now let's prove property number 3, which says as L increases, this is a non-increasing function. Okay. So again, to prove this, we have to show that H of U1, U2, U3, UL plus 1 divided by L plus 1 is less than equal to H of U1, U2, U3, UL divided by L. So let us start with H of U1, U2, U3, UL plus 1. Now this can be written as H of U1, U2, U3, UL plus H of UL plus 1 given U1, U2, U3, UL. Which property did we use? We used the chain rule. Now I am saying this is less than equal to H of U1, U2, U3, UL plus H of UL given U1, U2, U3, UL minus 1. Now which property did we use? We use the second property, which says as L increases, this is a non-increasing function. So this will be less than equal to this thing, right? Now we wrote this as H of entropy of U1, U2, UL plus uncertainty per letter. This is H of U1, U2, UL divided by L. Now which property did we use? Property number 1. Now this can be written as L times this H of L. So this is L plus 1 H L of U. So divide both sides by L plus 1. What we get is H of L plus 1 U is less than equal to H of L. So we have proved as L increases, this is a non-increasing function. What's the last property that we have to prove? That as L goes to infinity, this term is same as L goes to infinity, this term, which we are calling entropy rate. So clearly from the property 1, we can see that as L goes to infinity, this is less than equal to this. So what we need to show is as L goes to infinity, H of LU is less than equal to this, and then we will say both these conditions can only be satisfied when they are equal. That is how we are going to prove this, because from the property 1, as L goes to infinity, this is less than equal to this. To prove this, what we need to show is as L goes to infinity, this term is also less than equal to this, and then we will say both these conditions can only be satisfied when they are equal, right. So that's the proof, that's how we will prove it. This is slightly tricky, let's look at it. So first thing that we are saying is as L tends to infinity, this basically this limit exists, these limits exist. Why they exist? Because they are non-increasing function, so they are bounded from above. So basically, since H of LU and H of UL given U1, U2, U3 are greater than or equal to 0, and it is a non-increasing sequence, so they are always bounded basically. So they all have a limit. Now let us see what that limit is. Now from this property, we already know as L tends to infinity, this is less than equal to as L tends to infinity this. Now we are going to show you the other way around, that as L tends to infinity, H L of U is also less than equal to, when L tends to infinity, this term. So to show this, So, this obviously follows from property 1. So, let us prove the other way around. So, to prove this, what we are doing is we are taking the entropy of U1, U2, UL up to UL plus N. Okay. Now, this can be written as H of U1, U2, UL plus H of UL plus 1 given U1, U2, UL plus H of L plus 2 given U1, U2, UL plus 1 up to H of UL plus N given U1, U2, UL plus N minus 1. So, this follows from the chain rule. Now, this can be written as, this is upper bounded by H of U1, U2, UL plus N times H of UL plus 1 given U1, U2, U3, UL. How does this follow? This is a non-increasing function, so obviously this term will be the max of all the terms, and there are n such terms. So, this is n of upper bounded by n of H of UL plus 1 given U1, U2, U3, UL. Now, we are dividing both sides by n plus L. So, if we do that, on the left hand side we get this, on the right hand side we are getting this and this. Okay. Now, the trick comes. Instead of letting L go to infinity, we let first n go to infinity. Okay. If we let n go to infinity, what happens? This is a bounded term and this is going to infinity. So, this will be H infinity, which is the entropy rate, right. So, this will be basically entropy rate. Now, here what is this term? This is a bounded term, whereas the denominator is going to infinity. So, this will go to 0, and here you divide by n. So, 1 plus L by n. So, as n tends to infinity, L by n will go to 0. So, what you will be left with is this time 1 into this term, fine. So, I have so far shown you that this entropy rate is less than equal to this. Now, I will let L go to infinity. I will let L go to infinity. So, I let L go to infinity. Basically, what I have shown is this is less than equal to this. Okay. So, I have shown you this, and from the property 1 I have this. Now, both of them can be satisfied only there is a equality sign here, right. So, hence this, when L goes to infinity, this is equal to this is equal to what we call entropy rate of the discrete stationary source. So, that is the proof of this one. Okay. If you go back, we are using this fact that it is a stationary source. So, the distribution of U1, U2, UL is same as distribution of U2, U3, UL plus 1, or distribution of UN plus 1, UN plus 2, UN plus L. You have to remember this fact, because in addition to the fact that we are using that it is a conditioning cannot increase entropy, we are saying that distribution is stationary. So, no matter what your n is, they have the same distribution. That is why in the proof, when we are getting terms of the form UL given U2, U3, UL, we are saying that is same as we are decreasing L by 1, and that is the same. So, you have to remember that it is a discrete stationary source. So, U1, U2, UL has the same distribution as U2, U3, UL plus 1, and that is exploited here. So, if you look here, we start off with, so to show that it is non-increasing, we have to show as L increases, this term does not increase. So, this is less than equal to this. So, this is h of ul plus 1 given u1, u2, ul. Now, we are removing the conditioning on u1. So, that makes it h of ul plus 1 given u2, u3, ul. Now, we are making use of the fact that this is a stationary. So, we are replacing, let us say L by L plus 1, L by L minus 1. So, if we do that, so this is ul given u1, u2, u3, ul minus 1. Now, that will have same distribution because it is a stationary source, okay, and that is how we get this. Okay. So, we have proved some properties of this, basically how we describe uncertainty per letter for a discrete stationary source. And as I said, as L goes to infinity, basically both these measures of describing this uncertainty per letter is same, and this is denoted by what we call entropy rate of the discrete stationary source. Now, this essentially has the same role as your entropy had in your discrete memoryless sources. You will see that when we compute expected code word length for discrete stationary source, your entropy rate will pop up in similar way as your entropy plays in your discrete memoryless sources expression. We will show that expected code word length is basically lower bounded by this entropy rate. Okay. Now, let me go to this problem of coding these positive numbers using basically a prefix free coding, and this we are going to use in our next lecture when we talk about Elias-Williams code. There we will have to encode the positive numbers. So, we are in this lecture we are going to talk about how we can encode these positive numbers using some prefix free code, and we are going to talk about that Elias code. The first thing, let us talk about binary representation. So, in binary representation, how do you write the numbers? So, 1 will be 1, 2 will be 1 0, 3 will be 1 1, 4 will be 1 0 0, like that. What is nice about binary representation? It is compact. It is a compact description. Okay. Basically, number of bits required is floor of log n plus 1. It is a very compact representation. But what is the problem with binary representation? It is not a prefix free representation, right. So, 1 is part of 1 0, it is part of 1 1. So, it is not a prefix free code. And what is the problem with if it is not a prefix free code? You will have trouble if you are encoding positive numbers using a non prefix free code. We will have problem figuring out the basically what the numbers are, where the boundaries are essentially, right. So, the thing that we like about binary representation is it's very compact representation, but thing that we do not like about it is it's not a prefix free code. So, can we get a prefix free code, but then the number of bits required would be close to binary representation? That would be the ideal situation, right. Another thing that you should note here is binary representation starts with 1. So, that is like redundant, right. I mean, like any bit that you write in binary representation will always start with 1. Okay. So, maybe we can exploit that fact that when we are encoding using some code, we do not need to send 1, because we know by default first bit will be 1. Okay. So, this is binary representation. Now, let us talk about Elias code. So, what does Elias did? What Elias did was, so he took the binary representation, he prefixed it by runs of zeros, and what would be the length of that run? That is equal to number of bits required to represent that number in binary representation minus 1. So, for example, 1 in binary representation is 1. What's the length? 1. So the run of zeros will be 1 minus 1, 0. So the alias code 1 for 1 will be 1. Now let us look at 2. 2 in binary representation is 1, 0. What's the length of this code? 2. So the length of zeros preceding zeros will be 1. So it will be 0, 1, 0. Take 6. What's the binary representation of 6? 1, 1, 0. Now what's the length? 3. So you will have 2 zeros before that. So it will be 0, 0, 1, 1, 0. Look at number 8. Binary representation is 1, 0, 0, 4 bits. So the leading zeros will be 4 minus 1, 3. So it will be 0, 0, 0, 1, 0, 0, 0. Now what's the good thing about this code? It's now prefix free. How will you figure out which bit has been sent? You look at runs of zeros. From that you can guess what is the length of the number that is following. So if the run of 0 is 4, then you know that you have to look at next 5 bits and look at the binary representation of the next 5 bits, that is your number, correct. So that is the nice part about alias code 1. What is the bad part? You are almost using double this, because you have original length was ln, you are not using ln minus 1 zeros to pad up, right. So the length of the code word is now 2 times floor of log n plus 1. That is the bad part about this code. So it is a prefix free code, but then number of bits required is almost double of binary representation. My next question is, can we reduce it? Can we have a prefix free code which will probably have lesser number of bits than this code, alias code 1? The answer is yes. So let us look at alias code 2. So how does alias code 2 works? Alias code 2 begins with B1 code of ln. Earlier what were we doing? We were padding the binary representation by number of zeros of corresponding to length minus 1. Now what we are saying is, we are going, instead of padding them by zeros, we are now going to use B1 code. B1 code is the alias code 1 to denote the length. So we are not going to denote the length by runs of 0. Instead, we are going to use B1 code to denote that length. Okay. Alias code 2 begins with B1 code of the length of that binary representation of that number. So this will, so as a receiver, when it will receive B1 code of ln, it can figure out what ln is by decoding B1 code, and then it will know, okay, how many next bits it should look. Another thing what they did was, in alias code 2, it is followed by the binary representation of the number with leading 1 excluded. If you noticed, in binary representation of all these numbers, the 1 was common, right, 1 was common. Now what is done in alias code 2 is, to denote the length of the binary representation of number, use B1 code, and this is followed by the binary representation of the number, except the fact that leading 1 has been removed. Okay. So how will then the decoder decode? Decoder is first going to get, first part is B1 of ln. It can figure out what is the length ln is, correct. Once it figure out length, then it knows it needs to look at the next ln minus 1 bit. Why ln minus 1 bit? Because the leading 1 has been removed. So it will look at next ln minus 1 bit. whatever the number is, it will add a leading 1, that is your number. Okay. So, the decoder can figure out what bit has been sent, and the advantage of this code is, you will see the number of bits required will be less as n is, when n becomes bigger and bigger, this code will require lesser number of bits than B1 code. Okay. Now, let us look at few examples to illustrate it. Which number do you like? Okay, 5. 5 is 101, right. So, if the number is let us say 5, the binary representation of that is 101, correct. So, what is the length of this? Length of this is 3. So, the first thing I need to do is, I need to find the B1 code for 3. I need B1 code of 3. So, how do I find B1 code of 3? First, I need to write the binary representation of 3, which is 1 1. Now, what is the number of leading zeros? That is length minus 1. So, that would be only 1 0. So, B1 code of 3 will be 0 1 1, right. So, B2 code of 5 will be, initial portion will be B1 of 3, which is 0 1 1, right. Now, we are going to pad the binary representation of number with leading 1 removed. So, we are going to add 0 1, and that is what it is. You can see 0 1 1 0 1. Okay. Now, how will decoder figure out that this was 5? Okay. It knows the first number is B1 code of length. Okay. So, it starts to, so once it receives 0 1 1 0 1, so it knows the first code is B1 code of the length. So, there is a single 0, so it needs to look at next 2 bits. What are the next 2 bits? 1 1, that is 3, that is 3. So, it knows that it needs to look at next 3 bits, but obviously the leading one has been removed. So, it needs to look at next 2 bits. So, what are the next 2 bits? 0 1. So, what it will do is, in 0 1 it will pad that leading one. So, it will decode the number as 1 0 1. Is this clear? If you want, we can take another example, should we? Okay. Tell me any number. You can take a number which is not here also, that is not, but anyway. So, you want 7. So, let us say n is 7. So, first thing we need to do is, what is the binary representation of this 7? That is 1 1 1, right. What is the length of this? Is 3. Now, we need B1 code of 3. So, we need B1 code of 3. So, 3 is 1 1 and leading 0 will be only 1, right. This is B1 of 3. Now, to this number we need to pad the binary representation of 7 with leading 1 removed. So, I remove this 1. So, what I am left with? 1 1. So, this is my, you can see here, that is my B2 code of, this is the B2 code of 7. Okay. Is this clear how this works? Let us compute the length required. Why are we using, instead of leading zeros, why are we using B1 code to signal this? So, let us compute the length. Now, first part is B1 code of the length. So, number of bits required is length of B1 code for to represent L of n, and the next part is binary representation of the number with leading 1 removed. So, that is ln minus 1. Now, what is ln? Length of this is basically floor of log n plus 1. So, we need to find out what is the L1 of this number. Now, if you go back and see, in case of B1 code, L1 of n is given by 2 times floor of log n plus 1. So, if we replace n by log n plus 1, so basically n will be replaced by log n plus 1, right. So, this will become basically 2 times log of log n plus 1, okay, plus 1, and this log term, log n term. You understand how I am getting this? Because L1 of n is 2 times log n plus 1. So, n has been replaced by this. L1 of n is 2 times this floor of log n plus 1. So, n has now been replaced by this particular term, and this log n is coming here. So, what is the length now? I have a log n term and I have a log term plus 1. What was happening in B1 code? I was getting 2 times log n. So, now you can see one log n term has been replaced by log term. So, if n is large, log will be less, correct. So, are you convinced that this code will require for large n, this code will require lesser number of bits? Now, can you suggest a way to improve this code? I can use B2 code of the length ln instead of B1 code, okay, to signal the initial part, and then I will have this binary representation with leading 1 removed. So, what I will have is then log term, okay. So, if I repeat this process basically for large n, I will get that, okay. So, this alias code is nice in the sense it is prefix free, but then I mean of course, depending on which code you use to signal the initial length, you will get similarly log term or log term. So, you are kind of getting closer to binary representation, which is log n plus 1. Okay. So, this is how you can encode positive numbers using this one way of encoding the positive numbers using prefix free code. This is known as alias code. Okay. Any questions here? Okay. In the next lecture, we are going to use this coding of positive numbers and apply them for coding discrete stationary source using block to variable length coding. Okay. Thank you.